Hello everyone and welcome to Control Engineering Robotics and Mechatronics tutorials. In this tutorial series we explain how to sketch Bode plots of transfer functions by hand. In this particular tutorial we focus on a first order transfer function having this general form. To illustrate the sketching procedure with an example, we will consider this transfer function. And over here you can see the log magnitude plot of the transfer function, and you can see the log magnitude plots of its components. But before I start with explanations, I need to mention the following. Nowadays, we can use MATLAB or Python to generate Bode plots of transfer functions. However, it's still a good idea to learn how to sketch Bode plots of transfer functions by hand. Namely, by learning how to sketch Bode plots by hand, you will obtain a very important intuition about dynamical behavior of systems, about stability issues, and furthermore, you will also obtain some ideas on how to tune PID controllers as well as other controllers. Okay, let's immediately start. Our goal is to sketch a Bode plot of this transfer function. W of s is equal to 10 over s plus 0.5. Over here, s is the Laplace complex variable. The first step is to transform this function into this form. W of s is equal to k over 1 plus st, where k and t are constants that we need to determine. Now, how to do that? Well, we can write this transfer function like this. In the numerator we will have 10, and in the denominator we can take 0.5 out, and inside we will have 2s plus 1. Now, if we divide 10 by 0.5, we will actually obtain 20 over 2s plus 1. And here is our transfer function in this canonical form. The next step is to derive the sinusoidal transfer function. We obtain the sinusoidal transfer function by replacing s by j omega in this expression. That is, we substitute s by j omega, where j is the square root of -1, that is, j is the imaginary unit, and omega is the radial frequency. The radial frequency is expressed as 2 pi over the period of a sinusoidal signal, capital T. And it's measured in radians divided by seconds. So let's do that. We write W of s, when s is equal to j omega, becomes 20 over, what do we have over here? We have 2 omega j plus 1. And here is the sinusoidal transfer function. The next step is to transform this transfer function in the polar form. That is, to derive the polar form of this transfer function. So how to do that? Let's write it over here. W, now instead of s we will write j omega. And to derive the polar form, we will need to express the complex numbers in the numerator and the denominator in the polar form. Since the number in the numerator is a constant, its polar form is simply 20 multiplying e to the power 0j. That is, the modulus of this constant is simply 20 and the angle is 0. Let's write this complex number in the denominator in the polar form. The magnitude, or the absolute value, is the square root of real part squared plus imaginary part squared. Real part is simply 1, squared means 1, and the imaginary part is 2 omega. If we squared 2 omega, that is, if we compute the square, we will obtain 4 omega squared. And over here we will have e to the power of what? Well, we will need to compute the angle. In our case, the angle is inverse tangent or arctan, imaginary over real. So let's write it down over here. So it's arctan imaginary over real. Imaginary is 2 omega and the real is 1. And don't forget j over here. And that's it. Okay, now that we expressed both numbers in their polar form, we can easily derive the polar form of the complete transfer function. The polar form is 20 over square root of 1 plus 4 omega squared, and this is the magnitude of our transfer function. And let's write the angle part. We will have e, then what we will have over here, we will have 0 minus arctan 2 omega and everything multiplied by j. Here is the final expression of the polar form of our transfer function. From this polar form, we can retrieve the magnitude. The magnitude, denoted by capital M of omega, is 20 over this part over here, square root of 1 plus 4 omega squared. And we have the phase. The phase is usually denoted like this, phi of omega, or phi, however you like to pronounce this Greek letter, and it's equal to minus arctan of 2 omega. To summarize, m of omega is our magnitude and phi of omega is our phase. The Bode plot consists of two plots. The first plot is the plot of the log magnitude function. The log magnitude function, denoted by capital L, is defined as 20 multiplying logarithm with the base of 10 of m of omega, that is, of magnitude. And it consists of the phase plot. The phase plot is the plot of the function phase, that is the plot of phi of omega. Okay, let's start with the log magnitude function and the log magnitude plot. The log magnitude function is defined like this, and here is our magnitude. So let's compute this log magnitude function for our case. It's 20 log 10 of this function over here. 20 over square root of 1 plus 4 omega squared. And let's simplify this expression. This becomes 20 log 20 minus over here 20 log, and over here we have a square root of 1 plus 4 omega squared. We see that we can represent L as a sum of L1 plus L2, where L1 is 20 log 20, and this is approximately 26. What is the unit for L? The unit is decibels. That is, here is the unit, dB, or I will write it here, decibel, or S if you like the plural. And L2 is minus 20 log square root of 1 plus 4 omega squared. Good. Okay, let's start with sketching of log magnitude graphs. Over here I created 3 graphs. The first graph will be the graph for L1, The second graph will be the graph for L2, and the third graph is the graph for the sum of L1 plus L2, that is the graph for our final log magnitude function. But before we explain the sketching procedure, let's explain these graphs and x and y axes. First of all, you can observe here that the horizontal axis is in the logarithm scale. That is, our omega, or our radial frequency, is in log scale. You can see over here you have 10 to the power 0, 1, then you have 10 to the power 1, 10 to the power 2, and 10 to the power 3, and similarly you have 10 to the minus 1, 10 to the minus 2, and 10 to the minus 3. This is done in order to represent at the same graph and compactly large and small values. On the other hand, on the vertical axis, we have 20 log of m, or we have our log magnitude. And you can see that we start from 0, then we have 20 dB, 40 dB, minus 20 dB, and minus 40 dB. How you can read decibels? Namely, if you remember the definition, we had something like this. L is 20 log with the base of 10 of m. When the magnitude is equal to 10, that is when the amplification of our transfer function is 10, then you will see 20 dB. That is, when you see a 20 dB, you know that the amplification of the sinusoidal signals is actually 10, and this is very important. On the other hand, if you see minus 20 dB, you know that the attenuation of your m is actually 0.1. That is, if m is 0.1, this will be actually minus 20. And this is how you should understand decibels. Let's first graph L1. This is super easy. L1 is a constant that doesn't depend on the frequency, and consequently over here we will sketch a straight line. The line is located at 26 dBs. That is over here. And here's our L1. Simple as that, nothing special. Next, we explain how to sketch L2. We will sketch L2 by using asymptotes. And to define the asymptotes, we need to define one additional frequency. The name of this frequency is the break frequency. And I will write over here because this is very important. Break frequency. Break frequency is also called as corner frequency. And let's define this frequency. I will denote our corner frequency or the break frequency simply as WB. And WB is defined such that this term over here, that is the square root of 1 plus 4 omega squared, is equal to square root of 2. I will explain the reason for this later on. Now, if we take a square of this equation, we will obtain 1 plus 4 omega squared is equal to 2, or 4 omega squared is equal to 1, and from this equation we have omega squared is 1 over 4, and since omega is always positive, we obtain that omega b, or our break frequency, is 1 over 2. And here is the calculated break frequency. Here's the importance of our corner frequency. Namely, it can be shown when omega is much smaller than this corner frequency, this complete term over here becomes L2 can be approximated as minus 20 log square root of 1 plus very small number, and I'm going to denote it like this over here, just symbolically, and L2 can be approximated as minus 20 log of square root of 1, and this is equal to 0. That is when our frequencies are much smaller than the break frequency or the corner frequency. Our L2 is 0 in this graph, and this is an asymptote. And so let's sketch it over here. First of all, let's identify the corner or the break frequency. The corner or the break frequency is somewhere over here between 0.1 and 10. And in the logarithmic scale, it's most likely somewhere over here. And what we just concluded, when the frequencies are much smaller than this corner or the break frequency, the function L2 can be approximated as 0 in this scale over here. And over here I will do this, and this is our WB. On the other hand, when omega is much larger than omega b, we have this approximation. L2 can be approximated as minus 20 log, and let's see what do we have over here. Since omega is very large, this 1 can be neglected over here, and we will simply have here something that's very large and will be dominated by this term over here. That is, L2 can be approximated like this, minus 20 log 2 omega. Now, it can be shown that this function over here has a constant slope, and this slope is minus 20 dB per decade. We write it like this. So what does this thing mean? It means that if we increase our frequency 10 times, the function will decrease for minus 20. That is, it will decrease for this step over here, from here to here. And this is very important. And consequently, we conclude the following. After this point over here, we will have an asymptote that will behave like this function, and the slope will be minus 20 dB per decade. And let's sketch over here this slope such that we know the direction. Okay, so this is the direction, and then we need to draw a parallel line starting from omega b, and this line should be parallel to this slope over here. And let's do it, and here it is. And that's it. This is how we sketch L2 by using asymptotes. Now, next, at the break frequency, that is at this omega b, L2 becomes this thing, minus 20 log, and over here we will have square root of 2. Let's nicely write it down. And if you evaluate this expression, you will see that this is approximately minus 3.01 dB. And this is the maximum error that our asymptotes are creating. That is, over here, the actual value of our function L2 is here. And this is the maximum error we are making. So in reality, our function L2 will look like this. And I will sketch the function, and later on I will erase the graph since I don't want to make this graph to be too busy and messy. So in reality, the function L2 will look like this. And then over here we will approach this horizontal asymptotes. I'm trying to sketch the best I can on this computer screen. However, this might not be accurate. So let me do it again and try to do it better. Here it is. It approaches this asymptote, and over here it approaches the asymptote. And this is how the graph looks like. The maximum error is actually over here, and it's minus 3.1 dB. Okay, let's continue. Now that we know how to sketch L1 and L2, we simply need to add these two graphs to obtain our final L. So let's do that. What will happen over here? This constant over here will simply lift L2 vertically for 26 dB. And this asymptote will not be at 0 anymore, it's going to be at 26 dB. So let's do it over here. So over here I will have to have a straight line until our frequency, that is until here. So let's put it here, the break frequency. And we will have a straight graph until this frequency over here, or the straight line. And after this line over here, we have a new asymptote. That is, after the break frequency, our asymptote will go down with a slope of minus 20 dB per decade. That is, with this slope over here. So let's sketch it nicely. We just need to draw a line parallel to this line. And here it is. Okay, I'm doing the best I can on my computer screen, and it doesn't look bad. So over here we will have minus 20 dB per decade. And that's it. This is our graph, and if you want to make this graph to look nicer, over here you will put WB equal to 0.5, and that's it. Looks nice. Next, let's sketch the plot of our phase function. The phase function looks like this. Phi of omega is equal to minus arctan of 2 omega. We will sketch the phase on this graph. On the horizontal axis, we place the radial frequency in the logarithmic scale. On the vertical axis, we will plot the phase angle in degrees. Let's select a few characteristic points in order to sketch the phase function. The first characteristic point is obviously omega is equal to 0. When omega is equal to 0, our phase is phi of 0 is obviously equal to 0. And consequently, our phase plot will start from 0 point. Another point is when omega is equal to infinity. Phase at infinity is minus arctan of 2 multiplying infinity. And 2 multiplying infinity is again infinity. So we'll have arctan of infinity. And arctan of infinity is obviously pi over 2, and with this minus sign, we will get that phase at infinity is minus pi over 2. In degrees, minus pi over 2 is minus 90 degrees. And here it is. That is, we'll start here and we end here. Next, we know that arctan function is actually an increasing function of the argument. However, since we have a minus sign over here, we will have a decreasing function. Consequently, our phase should continuously decrease from 0 to minus 90. Next, let's select a third point in order to be able to sketch our phase. The third point is obviously the break frequency. Why is that? Well, when omega is equal to our break frequency, that is equal to 0.5, the phase becomes minus arctan over here, and let's see what do we have. We have 2 multiplying 0.5, 1, and that's equal to 1, right? So we have that phase is minus, what is arctan of 1? Arctan of 1 is pi over 4, and here it is. Consequently, our phase is minus pi over 4, and that's minus 45 degrees. Consequently, we have the third point over here at our break frequency. And now we are ready to sketch the phase function. Let's do that. Since the phase function is a decreasing function of time, we need to sketch a decreasing function. So let's do it from here. So we'll have that the phase will go down, go down, go down, go down. Let me now be careful over here. Then we have to pass through this point over here, like this. Then it will go like this, and it will asymptotically approach minus 90. And here it is. This is the best I could do on my computer screen. And that's it. Over here we have an asymptote at minus 90, and this graph should approach this asymptote. And that's it. This is our phase function. To be more precise, the phase function should look somehow like this. And the graph should be this way. That is, should be sketched like this. However, the graph scale is larger, so I had some issues. However, in reality, it should look like this. Okay, that's all for today, and thanks for watching.